Hello everyone, and welcome to our talk on hunting production memory leaks with heap sampling. So, who are we? My name is Ivo, and I've been doing stuff with Ruby since about 2014. And I always describe myself as a bit of a weird Rubyist because I've been doing a lot of work around performance and performance tooling, as well as I did a PhD and I did a lot of work with shared memory concurrency and whatnot. So I have an interesting background, I think. And that's how I ended up at Datadog, building Datadog's continuous profiler for Ruby, which is shipped as part of the DD Trace champ.
And my name is KJ. I work at Zendesk on our 1 million line Rails application thingy-majiggy. I'm relatively new to Ruby, so I kind of only started this stuff on our Rails app at end of last year. I'm focused on kind of the performance and reliability aspects of the monolith, and that means that I spend lots of my time looking at the profilers that he builds, which is kind of how we came to be introduced. All right. So what are we doing today? Firstly, we're going to go into a bit of background about what heap profiling is, what the existing solutions in the Ruby space are, and then we're going to talk about the work we did on the Ruby mem profiler gem and the backtracing gem to help enhance this space in Ruby. And finally, we're going to talk about where to go next after we do this work. Sorry, better clear my throat. OK, so when we're talking about heap profiling, what is it? So this kind of started for me because people would come up to me at Zendesk and ask me questions like this. They'd be like, help, my application's memory usage slowly increases over time, and whenever we do a deployment, it goes down again. I have some sort of memory leak. Or they might show me a picture like this, and it'd be, yes, my memory usage is suddenly it's fine, and then boom, shoots up in a giant spike, and the application gets killed. And they'd ask me for help on how to fix them, but these would always come with a big but, which is that but. These problems have a nasty habit of only wanting to happen on production. If you try and make it happen on your laptop where you can poke freely, where performance isn't a concern, sometimes they decide that they're going to chill out and not reveal the fact that they're a problem. So, putting on my not Ruby hat, I would reach for a heap profiler in another language like Go or C or whatever. So what a heap profiler would do is give us a point-in-time snapshot of the program's memory. For every object in the program, a heap profiler will tell us what is it? Is it a data object, a class object, an IMEMO object? What Ruby class does it belong to? How big the object is, and we want to know what code caused this thing to be allocated, because that'll be the thing that helps us know what to fix. So let's take, maybe best to explain this by example. We've got this great application, which I didn't pull straight out of Zendesk, and it's got two parts of it that allocate memory. So that top one is a very short-lived allocation, right? The ticket is loaded for that request, and it's going to go out of scope when the request finishes, and it'll get garbage collected probably in the next cycle. As Matt said, most objects die young. But there's a second kind of allocation there, which that is a global, and it's going to end up living forever. And so we've got ourselves a memory leak here. Every time this request happens, we leak a sum class. So a heap profiler of this situation would kind of look like this. You know, after a little bit of time, our memory looks like the thing on the left. So there's, you know, some stuff and the sum classes. And after more time, we have roughly the same amount of other stuff, but we've got plenty more sum classes because we keep adding them every time we make a request. And so a heap profile, if we get multiple heap profiles like this, we can subtract one from the other and come up with, you know, what has contributed to the growth of the memory in this process. And this helps solve our memory leak, because we can answer, what is it? Well, it's a sum class. How big is it? Let's say it's 40 bytes for argument's sake. And where did it come from? And we want to know, you know, what piece of code, what stack trace caused that object to happen. OK, so that's kind of the background. Let's talk about what's out there.
Okay, so obviously Ruby has been around for quite a bit of time, and people have run into this issue, and there are existing solutions for this issue. So there's Sam Saffron's great memory profiler and Shopify's heap profiler gems that kind of allow you to both gather information as well as have some list of top objects, most interesting things for you to investigate. There's gems such as derailed benchmarks, which is more focused on helping you like reproduce the issue by giving you a harness to re-execute your endpoints and your applications to try to figure out where is this coming from. And you have gems such as Heap, which given a heap dump, which we'll talk about next, will be able to kind of help you navigate that information, compare several heap dumps, etc. The key thing that unifies all of these gems is that the data gathering part is usually built on top of the ObjectSpace module and ObjectSpace extension that Ruby ships. So let's get a bit more into this part. So useful ObjectSpace API is that most of these gems in some way or another get their data from. One is ObjectSpace.traceObjectAllocationStart. So when you use this API, what it means is after you call it, from them on, like for every allocated object in your application, Ruby will also record the source file, the line, the method name, and a few more informations. And then you have ObjectSpace.dumpAll, which basically goes through your entire heap and dumps the contents of the heap as a JSON file. These two APIs work together. So if you enable trace object allocations and then you take a dump all, you will get on your heap dump the extra information that was gathered by the first API. So they kind of work together and get you a bunch of very useful information that those gems use. But there's a few challenges of using these APIs in production. For trace object allocation start, if you think about it, well, if we need to record extra information, that's extra memory usage that is added on top of every allocated object that you have on your application. Furthermore, the way this works internally is that basically Ruby will keep a big hash where the key to that hash will be the object, and the value will be the extra information. So not only you need to keep the extra information for every object, but you also need to keep a huge hash with like all of the keys and all of the values, and then you also need to remember to insert new objects into the hash and then remove them when they get garbage collected. So that's extra memory and extra CPU work. And as well as the part where we record the file, the line, etc. information can have a bit of a downside, which is like sometimes you may have like 50 or 100 different places in your application that allocate an object. But maybe all of those like 100 locations will call into a single method to do the actual allocation. So sometimes what you'll get is the information of the single method, not the 100 different places where it gets called from, which is probably what you're looking for to try to figure out what's up. And as well as ObjectSpace.dumpAll. So I would say the biggest downside of dumpAll is that it contains everything in Ruby heap. So it can contain security credentials that you're using to talk to the database or other services. It can contain personal identifiable information from your customers, which may fall under regulations such as Europe's GDPR, which may even say, okay, you are not allowed to download a heap dump from production to your developer laptop because that would go against those regulations. So, and it also can include other private business data. So it's like you need to figure out if you want to look at the heap dump from production, is it okay? How do you handle this data that might be very sensitive? As well as like these heap dumps may be hundreds of megabytes or even gigabytes in size. So if you have running your application in a container that's maybe ephemeral, you need to figure out, okay, where will I store this file? How do I save it? How do I access it later, etc. So it's a bit of a challenge, and since the file is big, it's an extra challenge. As well as when you're writing a heap dump, it actually pauses the app. So if you have a multi-threaded Puma web server or Sidekick with threads, when is a good time to pause your app? I don't know. And sometimes you actually want like multiple heap dumps to compare them. So now you need to figure out, okay, every 1 minute you have pauses in your app, and you have a gigabyte file that you need to put somewhere. So extra challenge. And this is kind of why we got to working on the Ruby Mem Profiler pprof gem. It's like, we want heap profiling, but like using ObjectSpace is kind of hard, so can we do it without ObjectSpace?
Yeah, so I rolled up my sleeve and we took a stab at this. The first implementation of a heap profiler suitable for production use, pretty textbook implementation of a heap profiler, right? So we started by keeping a hash, and we used the tracepoint API to get notified whenever objects are created with new obj or destroyed. So when a new object is created, the tracepoint will insert an entry into the hash over there and record what object it is and from whence it came, the backtrace. And then when the object is deleted, we remove it from the hash. And then we have a thread running in the background which periodically takes a snapshot of that hash and writes it to disk. And that's the profile. And so you end up with a file that tells you at various points in the program's execution what pieces of memory were around, what allocated them, how big they were, things like that. So the question of what we were going to actually write to disk is an interesting one, because you obviously don't want to be dealing with JSON or anything like that. It'll be very slow. So we ended up using pprof, which is an efficient binary protobuf encoding designed for performance profiling tools. Honestly, I think I picked this because the Datadog CPU profiler was already using it, and I'd looked at the code for that. So I'm like, great, go with that. But also, it's got some visualization tools for it already exist, right? So using an existing format would let us focus on how do we collect this information in an efficient way and punt on the problem of how do we visualize this in a sensible way until later. So for example, my not Ruby experience includes a bit of Go, and Go has a built-in thing for visualizing these files. So I wanted to generate something that I could just feed to GoTool pprof, basically. All right, so my textbook implementation was, about as slow as that GIF, which is not surprising. Because just like ObjectSpace, we were creating a giant hash of every object in the program. So we needed to get quite a few orders of magnitude of performance back. The first order of magnitude we got was by sampling. So instead of recording every object allocation in that hash, we will only, at random pick 1 or 2% of allocations to keep them in the hash. So that means that our new obj trace point almost all the time does nothing, and sometimes will insert things into the hash. Obviously, this makes the profile kind of meaningless on its own, but if you have a big fleet of servers in production, you could collect all the profile files and smush them together and come up with a nice average picture of what your application is doing. So that got us 1 order of magnitude. We needed a few more. So the next observation I made was that the profiler was spending quite a lot of its time Oh, OK. We have a streaming difficulty. We will be pausing it for a moment. Sorry. All right.
OK.
Where were we? No, let's go back a couple of bit. All right. So the story thus far, basically, we wanted to do heap profiling of Ruby applications in production, but existing solutions, I take this off, existing solutions built on top of the ObjectSpace module were not of suitable performance characteristics to be able to use in production. So we started working on a gem that did heap profiling outside of the ObjectSpace module. And just to refresh your memory, it basically was, oops, that's forward, not backwards. We put things into a hash when objects are allocated, to take them out of the hash when they're freed, and periodically flush the contents of that hash to a background thread. All right. So we're sampling 1 to 2% of allocations, and the problem that we came up with, even if we're only sampling, a few allocations, and mostly the trace point is doing nothing, it was still way too slow. And when I profiled the profiler using perf, it turned out that we were spending almost all of our time in thread backtrace locations, basically calculating those pretty backtrace strings to put in our profile output. So the quote solution quote we found with this was to have our C extension reach into the Ruby stack and manipulate or spy on the contents of the Ruby stack using all of the macros that are in the Ruby headers to basically emulate what thread locations is doing ordinarily, except we did it in our C extension. And because we needed it from C, we didn't need to do all the work of allocating Ruby strings, of allocating like the location structures, of joining Ruby strings together. So basically, we were able to kind of more efficiently calculate thread backtraces by getting the information straight out of the Ruby stack. So that got us probably one more order of magnitude extra performance, but we needed more. So the next observation that we made was that most objects die young. So very often, where we've got this, backtrace thing, and where we go to all this effort to compute these thread backtraces for objects that are almost certainly not going to live long enough to make it into a profile. Right? We're running the profile every minute. We might emit a profile file. So any object that gets created and then destroyed within that minute, we've computed its backtrace to then throw it straight in the bin. So the solution to that is to defer constructing the backtraces until we actually need to make the profile file. So instead of storing the backtraces as a string, what we can do is store kind of internal pointers to Ruby's data structures representing the instruction sequences, the callable method entries. So what we were keeping in our hash, instead of like a list of strings representing the frames, we were keeping the raw pointer to the Ruby, the part of the Ruby interpreter that had that controlled that piece of code. And then when we created the backtrace file, we would then stringify these threads, these backtraces. So that got us probably another order of magnitude of performance, and we still needed a bit more. So the next observation to make is that now that we're not constructing the backtraces until we go to create the profile file, the act of creating the profile file now takes quite a long time, and it blocks the global VM lock for quite a while doing that. So there's a twofold solution to this. First, what you can take out of the GVL, you take out of the GVL. So things like serializing protobufs, things like gzipping, that can all be done outside of Ruby in a separate thread without the GVL, so that's good. But the act of actually constructing a backtrace string from those raw ISEC pointers inherently involves poking around in Ruby's memory. You can't do that without the GVL if you don't want to crash. So what we did is we tried to make the profiler polite. So it would, we made some tremendously bad hacks to detect if another thread is trying to acquire the GVL, and if so, be polite, sleep for a while, let the other thread do its thing, and then come back later. The observation being that, constructing the profile doesn't need to be fast, it just doesn't need to get in the way of whatever else the process is doing that's probably more important. All right, so we did all of that. We went to all this effort of like hacking the Ruby interpreter in our extension to make it faster. Was it fast enough? Was this something that had performance characteristics that would be appropriate for production? So we had a micro benchmark. It was just allocating a whole bunch of objects and freeing them in various permutations. And what that was telling us was that at low sampling rates, we looked like we were going to be okay. That's only a 1% overhead or so for 1% sampling rate. And since we probably want 1 or 2% in production, that looks good. So then I dutifully ran cd zendesk gem install ruby mem profiler pprof, shipped it to our pre-production environment at Zendesk, and didn't quite go as planned. So if you look at the headline numbers, it's not amazing. If we sample 1 or 2% of memory allocations, our P95 latencies go up like quite a bit, up to 3 or 4, or maybe 2 or 3x as bad as they are normally. So this looks like a failure, but actually, I think I want to put on some more optimistic glasses than that, because this is within striking distance, right? If we were trying to do things based on ObjectSpace dump all, or do things based on trace object allocation in ObjectSpace, the response time there would be like seconds, not milliseconds. So this approach, I think, is close. With a bit more work, which we're going to go into in a while, this is something that it looks like an approach that could work for production with a bit more polishing. So although maybe it's not quite ready, I think this is, these numbers say that we're on the right track, hopefully, within striking distance. One sidebar I wanted to make, as we kind of went through that list of ways we improved performance of the extension, the Datadog native profiler, which is a profiler that Datadog give you for profiling C++ applications, also turned out to be quite useful for profiling Ruby extensions, because Ruby is a C program. So, I don't know if people commonly use like perf and perf-based tools to profile Ruby C extensions, but we did, and it was quite helpful. It was at finding, particular things like, allocating, getting the frame names for a backtrace or things like that were taking quite a while. So that's an approach that I didn't think about that you could use if you had a similar problem. All right, so we've gone to all of this effort to make this thing that performs OK. What does it spit out? So this is one of the flame graphs that we generated using, took one of the pprof files and ran it through the Go visualization tools that already existed. So we didn't make the visualizer here. And you read this basically as up, down is the call stack, and left, right, the width of left to right is how much memory that call stack allocated that was still alive at the moment this profile was taken. So that big horizontal block over there, that's like some method allocated a huge block of memory and held onto it for a long time. So that turned out to be 66 megabytes of GeoIP database that we load into Zendesk when we boot it up. I learned that doing this process. I think we can do not that, so I'll chalk that one up as a win to fix. But yeah, I think this is an example of the sorts of insights we can get from running our applications in production and looking at what the memory usage looks like with tools like this. You can try the gem. You bundle install it, and it comes with a wrapper script, so you can just wrap an existing application in it, and it'll do beautiful things to your application to make it periodically print out one of these files. And after your profile file appears, you can run it through a visualization tool, and you'll end up seeing something like this, showing what your application, what memory was live when the profile was taken in your application. So, yes, obviously I do not recommend running it in production, but if you do play around with this, please get in touch with us. We would love to know your experiences, use cases, etc., because I think this is something we want to keep working on. So please give us feedback. I think 1 or 2% is kind of what we're targeting with this. So you need to have a decent sized fleet in order to do this in production, I think. One thing I wanted to draw attention to finally is we spent a lot of effort in this project on backtraces. So I got in touch with Evo initially because I needed help mucking around in the Ruby C stack in order to construct backtraces really quickly. And Evo had been working on constructing backtraces really prettily. So you might notice these backtraces look quite a bit different to a normal Ruby backtrace. It's got the class name in there, the formatting is a bit different. So essentially, we've kind of wrapped up all this effort around backtrace construction, fast, pretty, etc., into a separate gem called backtracey, which might be useful for other profiling tools as well. So I'll hand it to Evo to talk about backtracey.
Thank you. So yeah, we built this backtracey to contain all of these things, and I can give you an interesting example. So consider this very simple application. It has a hello RubyKaigi module, print stacks class, and an initialize. And inside that initialize, we do two things. We print the regular Ruby backtrace, and we ask backtracey to also print a backtrace. And then we, at the bottom, we kind of call print stacks, which then calls print stacks.new, which then goes to the initialize. Pretty straightforward. If you look at the Ruby stack, you get this. Nothing particularly surprising. And if you look at the backtrace stack, you actually get this. But the interesting thing is if I do this and I hide the code, is that like the usual Ruby stack trace code gives you information, but doesn't give you a lot of context, especially if you're not looking at the code. So you see there, like, there's a new, there's an initialize, but what are we creating? What are we initializing? We see a times in there, like, maybe it's integer times, maybe not, how do we know, etc. And so backtracey tries to kind of solve this issue by making backtraces that are that have more information, especially when you don't have the context of the code. So you will see we have the module name, hello RubyKaigi. We have the class name, print stacks. We have, if you're calling a method on the class or module, we use a dot. If we're calling like initialize, which is like an instance method, we use a hash. So we can actually like show, oh, it's actually integer times, as I was expecting. So we get a lot more information, especially if you're not looking at the code. And there's even more things. So this is a very simple example. So in a nutshell, backtracing gets you like backtraces with extra information, and it actually can give you like the individual parts if you want to compose it, like print it in a different way. It has both the C as well as the Ruby level API. So obviously the Ruby BEM profiler pprofgem is using the C API. In my example, I was using the Ruby level API. The cool thing is that it works by directly accessing the Ruby VM call stack. So there's like when you load it, if you don't call it, there's no issue. So there's no overhead, no bulky patches, no trace points. Like it doesn't do anything. It actually only works when you call it. So zero cost if you're not using it, and you only kind of pay the cost of using it when you call it, which is cool. Internally, it's implemented, like Ruby has this RB profile frames API, and we basically took this API, copy-pasted it into the gem, kept the copyright, obviously, and then we massively modified it to be able to get all of the information we need, to be able to get lower overhead, et cetera, as KJ was talking about earlier. And yeah, we also experimented in seeing like how can we make this work on existing Ruby versions. And yes, we can actually make it work as far back as Ruby 2.3. Obviously, like the VM changes on every Ruby version, and so we have to have a lot of if-defs and different code paths for every Ruby version. But yeah, it was an interesting experiment, and it kind of worked. So let's go back to to heap profiling and talk about future ideas. So definitely performance is still the thing on our minds, and the cost of making turning the backtrace into a bunch of strings is still higher than we would like. So we're still exploring ideas such as what if we stored the existing names inside some of the internal Ruby objects so that we didn't have to keep generating them again and again. Another big cost is the cost of tracking live objects. We're still sampling, so it's still better than every object, but there's still some cost. So what if we could keep some profiling information alongside objects? Maybe with the variable with the location, that could be we could make a bit of space for it. So some things that we would like to explore around this. Also the cost of holding the JVL that we need during the profile construction. So here it would be interesting if we could make some of the information available so that you could access it without the JVL maybe, so that we could do all of the work without kind of blocking the Ruby code from keeping working. So that would be interesting. So there's a bit of a common thread here, which is it would be really interesting if the Ruby VM could better support these use cases. So at this moment, we basically had to build everything on the outside so that you can actually install this on a bunch of Ruby versions, and it will work. Right now, you don't need any patches or wherever. You can use it right now with your Ruby, which is our objective. But if Ruby had, Ruby already has a bunch of hooks and APIs for some of these things, but the problem is that usually they are not built for production usage that needs to be really, really, really low overhead. So it would be really nice if some of these APIs, more APIs were added, or these ones were expanded a bit with this use case of can we make it have really, really, really low overhead? Or even a crazy idea could be maybe Ruby could have its own built-in profiler. Other VMs like Java does this, Go does this, Node does this, and it has a few interesting properties when you kind of put a lot more of the profiling code inside the VM. So crazy idea. More interesting things to look at, visibility of things. So right now, we actually only track Ruby objects. So we don't track any of the native memory leaks. So if you are running a native gem and that gem is not properly cleaning up stuff, you will not be able to look at that with this gem. Also things like fragmentation, we were just talking about, malloc arenas, copy and write sharing, etc. These things would be maybe interesting to visualize, but right now it's only Ruby objects. Also, one thing that we would like to look into is reference chains. So right now we record where the object was created from, but sometimes you're kind of thinking, okay, why is this object still alive? Where is the object that is keeping a reference to this object? So this will help us answer that question. Some of the missing APIs that we would also like to have. So Ruby VM already has some internal APIs that we actually need to be able to get the low overhead we want, but they're not public. So there's a is pointer to heap that is really useful to make sure that something we are holding on to is still valid. Then there's rbgc disable no rest, which allows us to temporarily disable GC, but in a way that doesn't trigger GC as well. Both of these APIs are in the VM, but the VM does not expose this to extension. So again, we went to copy-paste code from the VM into our gem, and then, yes, it works. And as well as we had to create a few things that maybe could go in the VM, such as the API to see is there any Ruby thread that wants the JVL, so that we should kind of stop working now and let Ruby do its work. So yeah, that was it. Thank you, and thanks for putting up with the extra time with the technical issues. So both the Ruby Mem Profiler pprof gem as well as Backtracy are out on Ruby gems. And from my side, I'm working very hard to also bring heap profiling to Datadog's DD Trace gem, and we're hiring. Thank you.
Thank you.